All right. Let's see what we have here. Oh, we gotta get this. Better? All right. So, how are we doing so far? How many people have I scared? Here. Huh? Wake up. It's only noon. Yeah, I did, yes. That's why I'm kind of so light. I can move around. Have you all attended the recitations? How is it going so far? Good? Right. What's that?
The test was scary.
Which one?
The one that we took at the first recitation.
I would be shocked if you get 50% of that right. Okay? I would be pleased if you get 25% of it. The idea really, I mean, what I said in the beginning was that we are an accredited program. It's important for you to graduate from an accredited program, but when you talk about accreditation, we're talking about professional registration. So people recognize, it's like doctors, where your signature when you become a professional engineer is as valuable as a doctor. I mean, just imagine, you don't want to drive on a bridge that is not certified by one of us. You don't want to fly a plane that is not certified by one of us. So it is important to come from a program that is accredited, it is recognizable, it is Board of Education, and in fact we're expanding all over the world. So other countries are approaching us. The reason I say us because I'm part of the board. So part of that is the assessment, and which means that what I'm promising you, I want to make sure that first of all I deliver. Second of all, that you get, if not all of it, most of it. And then how do I do that? By basically measuring my performance. It's not by surveys that, I mean, you're going to get a survey, you're going to be commenting on the instructors and so forth. But really the best part of learning is to give you examples, things that we're doing here. And, we're measuring it up and see if you've learned it, if you can do the problem and, what that problem is and your understanding. Now, how many of you have got the clicker now? Most of you. I was hoping that I can run it here, but I'm not sure if I can do it because something is wrong. But let's start with the first one. In this one, I mean, you're supposed to give you your responses. I don't know what the hell is wrong here, but let's look at this problem. In this equation, do you all see this? Which one do you think is the right answer? All right, go on.
B.
E?
No, B.
B. Okay. How many people agree with him? You're the only one. No, actually, we got two more. So, 3 people go for B. Anything else? C? How many people with C? One of the you can't vote both ways. What is this? No, you got to buy lunch for everyone now. That's a punishment. But for one of you guys that gave the right answer, and I purposely wrote it this way because this does not follow the traditional y is equal to mx plus b, right? You wanted this to be minus 65.2 t plus whatever. And I didn't put that minus 65.2 because it was in the bracket to show you that this, in fact, is the slope. But when you're looking at that equation, which is minus 65.2 plus 83.9, do you think that this slope or this line, I guess everybody agrees that this is a line, right? Do you think that this line is actually increasing or decreasing? Yes. Why? Okay, so if that, which is a pretty good answer. So in your opinion, if this is representing a car, is it or is it coming to a stop? very quickly you are able to look at a mathematical equation and understand, physically understand it, okay? If it is representing a current, you expect that current to drop. Again, a mathematical representation of a physical model. And this is the whole thing. All we are doing here is relating mathematics to an engineering problem. All right? With the quadratic, we were looking at an equation that had two roots, right? Two real roots. And what I showed you was throwing a ball up, and obviously you could physically see that that ball goes through the same distance twice. Therefore, you have two roots. And there are other examples that obviously you saw in the homeworks. Any problems with the homeworks that could not be resolved in the recitations? We're going to put up the solutions there, so you will also see the solutions later on. How many people are visiting Blackboard? Good. Now, did you all receive the email from me about registering your clickers? All right. So that clicker is basically yours. If you're borrowing it from somebody else, you can always erase the data. But that basically, this clicker that you have is you. So you go to any classes and you press that TU ID number, and immediately we know that you have answered the question. And then the questions like this are important because it would give us an immediate, obviously we don't have a polling there, but immediate answer to my question, and that is how many of you are getting it. Okay? So the next thing is trig in engineering. Can somebody tell me what is trigonometry? Can somebody tell me what it is? Where is it coming from? What it stands for? Yeah, have you seen it? Yes, go on. Yeah, basically triangle. And that's the tri in the beginning is. But it has really applications, and many of you have seen that application. The easiest one that we can represent for you is called a linked robot or one link robot. Okay? It may look simple to you, but in fact, if you look at this, you see this in many, many places. If you look at a car engine, for example, that link could in fact be your crankshaft, which actually rotates and basically pushes the piston up. For those of you who might be familiar with engines, these are cylinders. You know, when you talk about 4-cylinder engine, 6-cylinder, you're talking about 4 or 6 cylinders that a piston is going up and down. And on it, there's a crankshaft, and the crankshaft is actually that one link. And why is it important? Because as this rotates, it is pushing something up and pulling it down. And that basically a mechanical movement. So why is it important that we have to understand this? Because this is the first basic principle of movement. Where do you see it? You see it in dynamics, you see it in mechanical vibration, you even see it in cells, for those of you who might be in bioengineering. So the principle of engineering is everywhere. Example, my hand, my arm, a prosthetic arm. Look at this. One link. Okay? So this link represents that. So what do we do with situations like this? What we do is we really want to find out the location. The location of what? So in other words, if I have a link like this, what is known to me is that length of that link, okay, and the angle that it makes, say with the horizontal axis. From there, I should be able to find out the location of the tip of that link, of that robot. It sounds silly, right, to call this a robot? Robot is a rigid body movement, and that's the simplest form of a robot. So what we need to know is if I give you the value of L, which is the length of that arm, and if I give you the angle of that, then what we need to know is the coordinates of the point, which is at the tip of that, which is X and Y. Now, can somebody tell me if we can actually calculate the coordinates of point P? Is there something that you might remember? Yes. Yeah, well, based on what? Is there a theory there? Is there a hypothesis? What is it? Have you learned something in the school that you might? Yeah? I mean, you said it, but it's coming from somewhere. Start with HYP. High. Yeah, there you are. There you are. You've seen it. But by physical observation, if I'm looking at this physically, what would happen as this arm moves, goes around that point, goes around? What happens to points P? What do they represent? What kind of shape will it make? A circle. A circle. So all these points actually lie on a circle of length L. All right? So as this is moving, these are making those locations. So when I'm looking at this movement, we're actually making a circle. Now, we need to come up with some form of a notation. Now, most probably you've seen this, that if it goes in a counterclockwise, it is positive. If it's clockwise, it's negative. You know, many times you ask that question, where did that come from? Because it always goes in this way, this has got to be positive, you know. Well, somebody, some smart guy out there decided that if it's going in this direction, it's going to be negative and, positive, and the other direction is negative. It really is irrelevant, but that's the principle that we have stuck with for centuries, and, we go by that. So as this arm is moving, is creating an angle theta, that if it is going in the counterclockwise, we call that theta as a positive direction. And if it's going in the counterclockwise, counterclockwise becomes a positive theta, and if it's a clockwise, it goes in a negative there. So if I am measuring theta, how do I measure it? Say from this point on the x-axis all the way to the negative x-axis. How do I measure that? Yeah, thanks. How do you measure angles? What's the unit of measurement for angle? Yeah. Degrees or radians. Does everybody understand what a radian is? All right, we'll get to that in a sec. So we're measuring it as a positive theta is this. What does that mean? Theta is what? How do we read this? Yes?
That basically the theta is above the x-axis.
Right. But how do you read this? What are we saying here? Greater or equal to 0 and less than or equal to 180, right? So in radian, then how do we measure that? Yes?
Maybe theta equal to 1 over pi, or pi over 4.
Pi over 4, yeah.
0, it's pi.
Pi, yeah. Pi. So we can represent this in radian as theta between 0 and pi. And on the negative side, how do we measure that? Theta would be, and somebody tell me, on the negative side? Yes.
Theta will be less than or equal to 360, greater than or equal to 180.
Okay. Okay, so if I write it this way, Does that make sense to you? Because we want to say negative theta, right? In what you said, there was no negative. So we're basically going this way from 0 to 180, and then we're going the other way from basically 0 to minus 180, which is exactly the same thing as you said, from 180 to 360. But what you were saying, it was positive direction, where we are talking about the negative direction. So in the pi version, or in the radian version, how do I write this? Yes, you want to say that? Go on. Okay, is that negative? No. Well, you want to say negative. If you want to say negative, what do you say? It would be greater than 0 and then less than or equal to minus pi. Right? So, there you are. So, I have a question for you. Why 360 degree? Where did that come from? The smart guy is going to be looking at their smartphones trying to get the answer. Yeah. Circumference of the circle is 360. Why do we say 360 degrees? Is that an arbitrary number? Does that make any physical sense? Yes.
I mean, like, there are 490 degrees.
Yeah, but where did it come from? Why not? I mean, if I were there and I'm, relatively intelligent, I would say, well, yeah, go ahead. One revolution, yeah, but why 360? Why not 400? Divided into 4 is 100 each. Is that simpler? Yeah. Someone made it up. There you are. If I were there, I would have said 400. But there's got to be a meaning to this too. But then, you talk about pi. Where did that come from? Where did pi come from? And it wasn't invented last year, It's been in existence for thousands of years. But where did pi come from? Yes?
Isn't that like the ratio between the diameter and the circumference?
Very good. Yeah. So actually pi has a physical meaning, where degree does not have any physical meaning. So if I want to show you what pi is, let's look at this. So if I have an angle, theta, and the radius r, do you know the relationship between these three? Actually, the actual curve. Can I measure S? Yes. Okay, or S is equal to r theta. Have you seen this? And theta in this case is in, what is the unit of theta in this formula? Radian. So you actually see there is a relationship between the angle, theta, and the radius and the length of that curve. So actually theta has a physical meaning. So in other words, if I want to show theta, I can say theta is S over R radian. Right? So if the S is the circumference of the circle. Now think about S as a whole circumference, as a full circle. What would S be equal to?
360.
No, in terms of radian. S. We're talking about the length of the curve. What is the circumference of a radius? I'm sorry, a circle. I'm sorry? 2 pi r. Right, 2 pi r. So basically in this case, you have theta as equal to 2 pi r over r. Agree? Or in fact, is simply equal to 2 pi. This is where this thing comes from. That the 360 degrees is in fact equal to 2 pi. So we have a measurement in radian that has a physical meaning, right? Which means that if I want to find the circumference of a circle, if I know the radius of that circle, think about the circle as a string going around. If I open it up and I measure it, the measurement is going to be 2 pi r, where pi is 3.14 and go on, and the rate. So has a physical meaning. Where 360 has no meaning. So some smart guy out there thought, well, why don't we just put 2 pi is equal to 360 degrees. If it was up to me, I would say 400. Make it much simpler. But that's, what we have to deal with. What is the dimension of radian? Is there a unit for radian? Is it measured in meters or anything? Look at it. No. Why? Because simply it's equal to S over R. S is in meter, R is in meter. So meter over meter is dimensionless. So radian is also dimensionless. But it is a factor. It is a physical factor that allows you to actually measure the curve. And the equivalency that we have between the theta and the 360 is a conversion factor that you have to remember. So why are we saying this? Because when you are trying to find positions of items in engineering, you need to understand the physical meaning of radian and why we are using that measurement instead of 360 degrees. Now, when it comes to other, terminology in this, obviously, both would work. So we want to find out if x and y of a point in this triangle, which represent that one link robot, are related to L and theta. Now, many of you might have seen this, right? How many of you have seen this relationship? Show me by your hand. How many of you have seen this? Where did we see it? Long time ago, in geometry. Yes. Yeah. But this is the hypotenuse theory, which means that L is equal to square root of x squared plus y squared. Do you agree with this? Have you seen it? Right. So we have also seen a terminology of cosine of theta is x over L. In hypotenuse theory, how do we describe cosine of theta? Yes. Exactly. Adjacent over hypotenuse, which basically is this, which from this relationship, I can find the length of hypotenuse as a relationship between x and theta. And the same thing goes when we have sine of theta. Again, using hypotenuse is the side opposite to the adjacent. All right? How many of you have seen this? Good. So what we need to do is now let's put the values into the equation up there. So what we have is x squared plus y squared is simply equals to, and then from the equation above, I'm replacing the value of x, I'm replacing the value of y, and this is what we have. So, in this case, in the first bracket, when you square L cos theta, what do you get? What do you get? L cos theta squared. What do you get? You square this. What do you get? L squared cos squared theta, right? L squared cos squared theta. In L sine theta squared. When you square that, what do you get? L squared sine. So we have L squared cos squared theta, L squared sine squared theta. Is there anything I can do to that equation? Is there? Yes.
Equal out the L and then just add the cosine squared.
Do I get? Do I factorize only L? L squared, right? Yeah, that's right. I know that's what you meant. But if I factorize it, this is what I get. L squared cos theta, cos squared theta plus sine squared theta is equal to L squared. Where did I get this L squared from? Remember that? Up there. Up there. So if I'm comparing these two, what conclusion do I make? Remember, when we say hypotenuse formula, the equation was L is equal to the square root of x squared plus y squared. If I square that, I have L squared is equal to x squared plus y squared. Okay? So if I compare the two sides of this equation, what conclusion do I make? Yes?
X squared plus y squared equals L squared.
And that's the same equation that we have up there. But also we have another observation. Another observation is this, inside the bracket. What is that equal to? Yes?
Cosine squared theta plus sine squared theta equals 1.
That's right. All right, and you most probably have seen this at one point or another. Any questions? So, what we are showing you here is the relationship in the trig basis of cosines and sines. So the first thing you learned here is cosine squared of theta plus sine squared theta is equal to 1. So other terminologies that we use are tan theta, tangent theta. Have you seen this? If you remember that triangle, x, y, and L, tan theta is sine of theta over cosine of theta, which is simply y over x. It's always a problem with finding a pen here, yeah. So, theta, y, x, L. Tan of theta is y over x. Have you seen this relationship? We also have this. Can somebody tell me what sec of theta stands for? Yes. Secant, right. Where it came from, I have no idea. Somebody wanted to mess with us. And what about CSC? Cosecant, yeah. Well, isn't it interesting that he says secant of theta is 1 over cos of theta? I mean, you would have imagined that, well, secant of theta should be related to sine, right? Because they all both start with S, which is not true. But then when I'm looking at these two, what kind of relationship do you think I can get out of this secant and cosecant? Yes?
They're the reciprocals of our previous equation.
Right. So basically, if I say 1 over cosecant square plus 1 over secant square is equal to what? 1. Why? Because 1 over secant is simply sine squared, and this is simply cos squared is equal to 1. Again, these are mathematical manipulation of the same thing. As far as you're concerned, what is really important for you are sine, cosine, and tangent. And there's a reason for tangent. Later on, you will find out that the tangent has a relationship to the slope. So what about this one? What does this stand for? Cotangent, exactly. Cotangent, which is basically an inverse of the tangent. All right, so now we have learned that sine squared plus cosine squared is equal to 1. We have tan of theta as y over x. So can I start finding out the locations? So let's say for a theta of 0 and 90 and minus 90 and plus and minus 180, we want to find out the value of x, y, cosine of theta, and sine theta. So the first thing is theta is equal to 0. See that rigid bar? Right now. So physically speaking, if I just inspect it, what do you think x is here? The value of x. The point P is the tip of this arm. Yes. L. Right. What is the value of y? 0. So basically by inspection, we can simply say x is equal to L and y is equal to 0. Do anyone follow this? So this is just by physical interpretation. So if I say x is equal to L cos of 0 degree is equal to L, why is that? Physically, we're saying that x is equal to L, right? Yes?
Cosine of 0 is 1.
Yes, there you are. Do you see that? So immediately we find out that cosine of 0 is equal to 1 because physically speaking, x is equal to L. Therefore, cosine of 0 cannot be anything but 1. So cosine of 0 degree is equal to 1. What about y? What is the value of y? Yes? 0. Right. Where is y? Right here. Because we are measuring the tip. So y is equal to 0. So physically speaking, y is equal to 0. So y is equal to L sine of 0 is 0. What does that tell you? Sine of 0 is 0 because L cannot be 0. So cosine of 0 is 1 and sine of 0 is 0. So we are beginning to make sense of the physical meaning of these angles. So now we are moving. Now we want to move the arm to 90 degrees. So now I'm looking at the tip of that arm. What is the value of x? 0. Physically, x is equal to 0. And y? So by inspection, x is equal to 0 and y is equal to L. Which basically means that x, which is L cos of 90 degree, is equal to 0. Why?
Because cosine of 90 is 0.
There you go. Does anyone follow this? Good. All right. So then we go with the y. Y is equal to L sine of 90 degree. Yes. There you are. Sine of 90 degree is equal to 1. Easy, right? So now we're going to move it again. Now I'm going to take it to minus 90 degrees. right here. So it moves all the way down. So physically, you see this? Minus pi over 2 radian, or theta is minus 90 degree. Is there another way I could have represented this? Another value for theta? Yes, 270, right? And then for, in radian, what's that? 3 pi over 2. Does everyone understand that? So they're both the same. One goes in this direction, the other one goes the other direction. So in this case, what is the value of x? Do you agree? Why? Go on. Yeah, it's in the middle. That's a good answer. Yeah. Physically, you can see x is 0. Physically. So I can just simply write it as x equal to 0 and y is equal to minus L. Where did that come from? I know, right there, but explain. I know, but you have to understand, this is positive x direction, this is negative x direction. This is positive y direction, and this is negative y direction. That's why it's called minus L. So in this case, if x is equal to 0, L cos of minus 90 degree is equal to 0. So from there, what do you find? Yes. Do you see a relationship between cosine of negative 90 degree and cosine of 90 degree? Do you remember cosine of 90 degree was 0? Very simple, because this was up here. Which simply means that cosine, if you remember that triangle, cosine was what? X over L. And in this case, x is 0 in both cases. So it doesn't really matter whether you are in the minus 90 or you are in the plus 90. X is still 0. And therefore, if it's x is equal to 0, cosine is 0. What about this one? What do you get out of there? That this is equal to minus L. Yes? Negative 1. All right? There you go. Now, in your opinion, do you think you can do theta for 180? If it was 180, which means this was here, what would the x be?
Negative L.
Okay. Y? Right? Cosine of the angle, cosine of 180 would be? Negative 1. There you are. Just like that. All right? So I'm not going to go over that. So let's look at another problem. Now we're going to make it a little bit more complicated. We're going to look at the 45 degree, minus 45, 135, and minus 135. Okay, the first one is this. So by inspection, can you tell me what x and y is? Just by inspection. Yes. X is L? Do you agree? It can't be L because L is that big one and X is the small one. So they're not equal. So in this problem, yes. You want an answer? X equal to y? Yes, it is x equal to y, but that doesn't give me the answer. So in this case, you really need to use what you have learned. And that what you have learned is this, that x is equal to L cosine of 45 degree. Cosine of 45 degree, and the cosine of 45 degree is 1 over square root of 2, or simply L over square root of 2. Now, your math teacher at high school, did he or she allow you to have a square root in the denominator? No. Why? Oh, they had an attitude problem. I have no problem with that. Put a square root down there. It really has no meaning. It doesn't matter because square root of 2 is still a number. But if you want to put it up there, what do? Yeah, multiply it by root 2. So what we would have is L square root of 2 over 2, which is exactly the same thing as what we have here. So this would be the value of x. Can somebody tell me what that value is? Calculator? Square root of 2? Come on, let's see if you're faster than me. 1.41. Come on, continues. Right, so that's why we leave it like this, because if you want to put it in fraction, it's going to go on forever. Right? So this would be x. So what is y? What is y equal to? What is y equal to? Look at that triangle here. Y is equal to. Y comes from sine. Sine of theta is y over L. Therefore, y is equal to L sine theta. Now, did somebody say that x and y are equal? Yeah, so I can't expect anything by this. Because sine and cosine of 45 degree is the same. And it is obvious because that creates a square right there. Therefore, from here, the coordinates of the tip of that robot are L over square root of 2 and L over square root of 2, forming a square. So if I change this robot into a minus 45 degree, now physically, now you have the answer over there. And you have this problem. Yes?
Why don't you just flip it and transition it over to surface, or why don't you just make the x value a negative and that would be the same thing?
Right, so would the x be negative here?
No, why would
Y would be negative, yeah. So again, you already know the answer because you already did this. So you are already making up your mind about what the answer should be. And this is really a very important exercise in engineering. Because in engineering, we are talking about practicality. We are talking about logic. So even if you use a calculator or something else, you should be expecting the answer. What kind of answer you would expect. So if I'm following the formula, all I have to do is just say x is equal to cosine of minus 45 degrees. Y is equal to L sine of minus 45 degree, and I will get the same answer. But you already knew the answer. Isn't that amazing? You already knew the answer without even going through this mathematical calculations. So the physical interpretation of the system is important when it comes to mathematical calculations. You remember one thing in your engineering career. Garbage in, garbage out. Very important that whatever we input into our system is an accurate input. And the expectations are realistic. I've had people that, been working for me and then they come back with exaggerated numbers that, this 3 times the speed of, light when it comes to a rocket engine or something. But you got to use your own logic. Is that possible? In this case, I could physically tell you what to expect. And then you obviously got what you expect. So, if I'm moving it here, can you tell me just physically what the x would be? Yes?
Negative L over root 2.
Yeah. So it's the same as 45 degree, except it's on the negative side. And the y? That's right. So we do the same thing. There you are. So obviously I don't have to do this. Right? You can do it on your own. Any questions so far? So when we are dealing with functions like this, we have to memorize one thing. And one thing is that the values of sine, theta, cos theta, and all other trigonometric functions depend on the quad and the reference angles. We divide the system into 4 quadrants. Quadrants are, if you think about this circle going around, there are 4 quadrants there between x and y. The first quadrant, what is the value of sine theta and cos theta? Are they positive or negative? Yes, positive, right. So in the first quadrant, we have positive sine theta and positive cos theta. In the second quadrant, what is the value of sine and cosine? Yes. Okay, can somebody tell me why sine is positive? Yes. That's right. Y value is positive. Very good answer. Therefore, this is what I expect. In the third quadrant, what do we have? Both negative. Why? Both x and y are negative. And the fourth quadrant? What is the sine theta? What about cosine theta? Y? X positive. There you are. So, this should really be engraved in your brain, because that would be your basic logic, that when you are dealing with angular measurements, all you need to do is remember this, and then when you are calculating the values of sines and cosines and otherwise, you would then expect, what is coming your way. So very normal for us to even remember this, that we do have some reference angles, but that we have to remember. These are the reference angles. I've put it both in degrees and in radians. 0, 30, 45, 60, and 90. If you have this, you almost know every answer for trigonometric operations, because there's no other angle that will not fall within this. Why? Because we just found out that the relationship between thetas and minus thetas. So if I'm looking at, say, 45 degree angle, all I have to do is just remember the 45 degree angle, because I can then find out minus 45 degree or 135 degree or 235. Do you see that? Because all I have to do is just remember the first quadrant, and these are the values, and they're easily memorized. You already know the 0 and 90 degree. The 45 degree we found out, and then all you have to do is 30 and 60 degrees. And you can just see the relationship between 30 and 60. You see this? They are opposite. Sine of 30-degree angle is half. Cosine of 60 degree is half. Cosine of 30 degrees, root 3 over 2. Sine of 60 degree, root 3 over 2. And obviously, the rest is right in front of you. Any questions so far? I guess I have to let you go at 12:50. On Friday, unfortunately, I'm attending a meeting, but my TA will be teaching here for me. So don't panic. Again, I will answer your questions if you have any. And obviously, you know what your homeworks are. This week, you will have your first lab as well, right? No, next week, sorry. Next week, you will have your first lab. Friday, you will show up here. Okay? Good luck.
Collected by the recitations, right?
I'm sorry?
Homework is collected in the recitations.
Yes. Yeah.
By the way, remember there, I saw the link to the pre-engineering survey,
Uh-huh.
and it's like since last week I saw that it was wrong. I don't. So that was that taken down? Or?
I think it's gone, yeah.
I mean, I saw that it disappeared on Friday.
Well, I guess the survey was supposed to be filled by then, right?
Yeah, I guess.
I couldn't go to my recitation last week because when I tried to find the room number on Blackboard was down for
No.
most of the time. But
Just
then
let your guy know. But do you have any problems?
no, not now, not anymore.
Okay, just let him know because of what the reason was.
Thank you.
I had an issue because I was used to, like, instead of 1 over root 2, I was used to
Root 2 over 2? Yeah.
So that's why I got that question in the test drawing in like 2 tests.
Don't worry about it. That test doesn't count.
Yeah, that's true.
Doesn't count.
But it's okay if I use that.
Oh, yeah. Absolutely. Yeah.